that it lines up with application, presentation, and session. So again, that's what we'll be discussing. The application layer is the closest to the end user. Network applications enable users to send and receive data with ease. Application layer acts as your interface. It lets you exchange data between your source and destination hosts. And we already talked about how the application layer of the OSI model is really lining up, or the TCP IP model lines up with 3 layers in the OSI model: session, presentation, and application. We will be discussing in this chapter a bit on the HTTP hypertext transfer protocol, file transfer protocol, trivial file transfer protocol, and DNS. We have specific sections for DNS, DHCP, HTTP coming up here in just a moment. So first thing we're going to take a look at is the presentation layer, basically formatting data so it can be displayed on your device so you can interact with it appropriately. You can see the 3 main functions are formatting, compressing data, and encrypting data. So again, formatting is just going to, format the data in a compatible format for your destination or source device, really your destination device that's receiving the data. Okay, compression is just compression. If data can be compressed, it will be compressed at the presentation layer and decompressed at the presentation layer. Encryption of data, we've talked about data encryption. That'll happen here at the presentation layer as well. Some formats that will be compressed, formatted, encrypted, decrypted are MPEG, which we'd use for video. We've got GIFs for pictures, JPEGs for pictures, PNGs for pictures. There's going to be some type of formatting that lets you view those on your computer. The presentation layer is going to take care of that. Okay, not too much to the presentation layer here. We have the session layer as well, which is gonna maybe confuse a little bit, but don't let it confuse, because it sounds a lot like the transport layer, which we just discussed in the last chapter. It says the session layer creates and maintains dialogues between the source and destination applications. We said that was the job of the transport layer last chapter. The session layer handles the exchange of information to initiate dialogues, keep them active, restart sessions that are disrupted or idle for a long period of time. Yes, it does do that. So the session layer has that responsibility. The transport layer is what adds your transport header with your port numbers that the session layer handles. Okay, so it adds that information, but really the session layer, semi in conjunction with the transport layer, is responsible for keeping sessions active, restarting them, so on and so forth. So if in a test you are asked which layer is responsible for this, that, and the other, the session layer is responsible for keeping conversations active, restarting sessions, and initiating sessions. Okay, the transport layer really is just adding your port numbers on and getting the segment ready so that the session layer can receive it. Okay, so there's a little bit of confusion there in the readings, because it does make it seem like the transport layer is responsible for maintaining the data, for maintaining the conversation, but really it's putting labels on the conversation so it can be maintained. It's really the session layer's job to maintain the conversation. We've got some TCP IP application layer protocols here and some examples of them. Those protocols must be implemented on both your source and destination devices for it to work. And the protocols implemented on the source and destination must be compatible to allow communication. We saw a few of these protocols in the last chapter, of which we were discussing TCP versus UDP in the transport layer. So you have domain name service, dynamic host transfer, configuration protocol, so on and so forth, email, file transfer. And we'll talk about some of these as we move through the chapter. Right, how applicational protocols interact with the end user. Client-server model, we've discussed the client-server model. You've got a client that is requesting some information and a server that's responding to that request. A client and server doesn't necessarily have to be actually a PC and a actual server. Any device that is responding to a request for communication, for information, can be considered a server. So it doesn't have to be an actual server here. Okay, so we've talked about the client-server model before, back in chapter 2 or 1, I forget which one. So I'm not really going to spend much time here on the client-server model. Peer-to-peer, we've discussed as well. Peer-to-peer, you don't have one device acting as the device that responds to requests for information and one device that's just requesting the information. Here, they can play both roles. So you can ask for information from this computer, Peer 1, or you can respond to a request from Peer 1 as well. So they're performing both the functions of a client and a server in a peer-to-peer network. So that's what peer-to-peer is. We've discussed the benefits and drawbacks of peer-to-peer versus client-server earlier in the course. We've got some hybrid peer-to-peer applications that are peer-to-peer. There's just some type of server in the middle acting as an index to point you to where the information you're looking for is at. Okay, contains an index that will point you towards where your information is located. You still have a peer-to-peer situation where both devices are acting as a client and a server, but there is a somewhat of a server in the middle that's pointing you towards the right direction for the information you're looking for. Okay, so instant messaging would be an example of that. On the next slide, we have some older programs like eDonkey and G2. Bitcoin's still around, BitTorrent's still around. Those are peer-to-peer services that have a index in the middle letting you know where you can go to get the files that you're looking for. So those are hybrid peer-to-peer services. I believe we've discussed BitTorrent here before. Basically, if you have some program or some file that you want to share, many peers will all have a piece of that file, and you can grab those pieces of files from maybe 100 different people and assemble the whole file eventually, or the whole movie, song, program, whatever it is you might be looking for on BitTorrent. It's actually a pretty efficient application. It's not always used legally. So that's why it gets a bad rap, the BitTorrent application. We have some well-known application layer protocols and services that we'll go through. Web and email. HTTP, or Hypertext Transfer Protocol, is what we have on this slide, and the process it uses to deliver a web page or a requested web page. URLs here are discussed, which are uniform resource locators, basically what you type into a web browser to get your web page, or a URI, a uniform resource identifier. You've got three parts of your URL. You've got the protocol or scheme, which would be the HTTP, or sometimes HTTPS. Server name, something.com, .org, .net, something like that. And then the specific file name requested, which you don't even typically type in yourself. That index.html would typically be your home page for that specific website. So you type that all in, and you get a web page back because, well, you're sent this index.html file, or whatever file is sent back in HTML code, and the application on your computer, the browser, is able to decode that and present it to you as the web page. Okay, how we actually end up getting it, or how this gets resolved to a normal IP address, this URL, is through DNS, which we've discussed earlier in the class at some point. I don't forget which chapter. But basically, when you send a DNS request, it takes that URL and turns it into a normal IP address, like something like 10.40.110.32 or something like that. You do need the actual IP address to contact a website. It's just we don't have to type it in ourselves because we can use these URLs and we have DNS servers to do that work for us. So that step one would be to get the DNS resolution of your URL. Then your client is going to send a GET request to the server's IP address asking for a certain file. The server is going to respond, and it may look like code something like this. Okay, as it's being sent back to your computer, your client's going to receive this HTML code and format it so that it looks like the web page you requested. Okay, of course you don't want to see this HTML code when it arrives back at your computer. All right, so that's the whole process. DNS, you gotta send a GET request to the server. Server sends back the requested page in HTML code, and then your browser is going to decode it and format it so that it becomes the web page you see in front of you. We have HTTP versus HTTPS. HTTP is not secure. If someone were to be sniffing your line with even a program like Wireshark, which we've used in class, they could tell what you were doing with the HTTP and intercept that data. So it's not a secure protocol. It is a request-response protocol, and it has three different types of messages. The three messages are GET, when you're requesting information from a web server. Okay, so browser or client is requesting information. We had a GET in that last slide, I believe. Post is going to be when you are uploading files to the web server, updating forms, text, things of that nature. And put is going to be more for content like pictures or maybe video, things like that that you're going to put on the web servers. So those are your three common message types. GET to request information, post to update text basically, or forms on the website, and put for content like graphics, videos, things of that nature. Okay, it's not secure. Messages can be intercepted, but if you want to be secure, you'd use HTTPS because there is encryption involved in HTTPS. That's when you, just about any website where you're going to be spending money, entering in credit card information, you will see that it is HTTPS and not HTTP. Next, we have our email protocols and how email breaks down, basically. Our different protocols are SMTP, POP, and IMAP, and we'll talk about the difference between those. But how email works in general, if you don't know, is that you never communicate directly with your recipient. You don't just send an email and then it arrives at their station like for instance, a peer-to-peer type of application runs. Your email is sent to your email server first. So let's say that this sender is on Verizon and this sender is on Time Warner. Okay, I don't know who's getting the better end of that deal, but anyway, so this sender sends an email to the recipient. It goes to Verizon's server and sits there for a second. Verizon's server tries to see if Time Warner's is there. If it is, it's going to go ahead and send that mail to Time Warner's server. It's going to be held there until the recipient goes ahead and checks that email. And depending on whether he's using POP to retrieve or IMAP, one of two things will happen. But we'll talk about those later. Basically, he's going to end up receiving the email either way. It's just depending on whether he's using POP or IMAP, the email will be sent from the server to his station, and it will be removed from the server using POP by default. Or if he's using IMAP, the message will be kept on the server. He'll basically be browsing it from his computer on the server, and it's stored there on the server rather than being sent to his computer and being erased from the server. Okay, so they don't communicate directly. If the sender's server can't communicate with the recipient server, after a while they'll get a message bounce back that tells them the server is unreachable. You've probably gotten a message like that from time to time that says source or destination address unreachable when you send out a email. So that's what's happening. Their mail server is not reachable for some reason. SMTP, or Simple Mail Transfer Protocol, is what you use to send email. The email just has to have a body of the message and a header. And the header has to have an appropriate email address, and otherwise it can't be sent. Okay, so this is what you're using to send your emails. It is on port 25. That is a well-known port. That is a port that you will want to remember for your exams going forward. Okay, in fact, you should have remembered it from last chapter, because I believe that's when, is that when we discussed ports? Probably. One of our chapters, either 9 or 10, I mean 8 or 9, definitely 9, we talked about ports and the ones you're supposed to remember. Anyways, as you send out that email, it's going to go to a mail server. It may need to forward it to another one till it gets to the recipient's mail server and it's stored there. And then one of two protocols is going to be used when the message is on the recipient's server, either IMAP or POP. POP is what we have on the next slide. So on POP, you need to know that POP, Post Office Protocol is what that is on port 110, and messages are downloaded from the server to the client, meaning that they're not on the server anymore. So if you use default settings for POP and say you download your email to your phone from the server, you want to get on your computer and check that email and do something with it, it's not on the server anymore. Okay, that's not something that's set in stone. On many POP servers, you can choose to leave a copy of the message on the POP server, even though you've downloaded it. So that's what most services will actually do, it seems like these days, is they'll leave a copy on the server, or at least have the option for you to leave a copy on the server rather than just remove it and place it on your computer. Okay. There's no centralized location where email messages are kept. The downloaded messages resides on the device that triggered the download only. Again, this is only by default. It doesn't have to be that way. There are options to leave the mail on the server as well these days. So, but for the course materials, I guess forget about that. For the purposes of testing, POP removes your message from the server and it's no longer there anymore. That's what the test is going to say. So just realize that. Even though in real life, POP, there is an option usually to leave it on the server. For test purposes, no it doesn't. It just puts it on your device and it's gone from the email server. Again, it's a well-known port, port 110. Remember that port. IMAP is, well, kind of the opposite of POP in that it leaves the message on the server and you're just managing your email on the server. So anything you make, any changes you make to your inbox, if you're creating new folders, moving messages from place to place, all that is happening on your server and on your computer. So they're basically mirroring each other. That's what IMAP is. You can think of it as one mapping to the other, always reflecting the other. Okay, so you can use a organized folder hierarchy on the server to organize your mail. File structure is displayed on the email client. When a user decides to delete a message, the server synchronizes that action and deletes the message from the server. So if you delete it on your device, it'll delete from the server. Okay, so that you're viewing copies of your messages on the client. Basically things we've talked about. Okay, messages will stay on the server until they're manually deleted, because that's where they're stored by default in IMAP. Okay, so that's the nature of IMAP. It leaves the message on the server. You manage everything on the server side. Everything you do on your computer is just being reflected on the server. Okay. And IP addressing, no, it's not what you're thinking. It's not more subnetting. Don't worry. All right. DNS, we've talked about domain name service. So again, we've talked about domain name service a little bit. You have some URL that you typically will type in, or domain name. For instance, a domain name would be something like www.cisco.com here, easy for us to type in, or something like www.google.com. But that's not what our computer sees. The computer, or uses to communicate, I should say. The computer actually needs the real numbered address of a web server website. Okay, so it has to use DNS to figure out what that is. There we go. So when your device is trying to communicate with a domain like cisco.com or google.com, something like that, the first message that's going to go out, well, if it's not an ARP request, like we've seen in Packet Tracer as we've generated traffic and observed it, one of the first things that's going to happen is a DNS request, or a DNS query, I should say. You're going to go to the DNS server and try to figure out what the IP address is for the domain that you typed in. Okay, so this is a DNS protocol. Communications use a single format called a message. So a DNS message is sent out. A DNS message comes back. Okay. So DNS supports 4 different types of messages. You've got your IPv4, which is just an A. You've got an authoritative name server, which is an NS. You've got your Quad A, yes, pronounced Quad A, which is for your IPv6 addresses. You got MX for your mail exchange record. Okay, so those are the types of records that are supported. So that when your message goes to the DNS server, we'll first look at the server itself. Will first look at its own records to resolve the name. If it's unable to resolve the name, it will basically send that request up the tree of servers to find out what the name is. And there is a hierarchical tree of servers that will receive that request and respond to it eventually out there. Okay. The response is then forwarded to the requesting client. The DNS client on a Windows PC also stores previously resolved DNS addresses. Okay, if you want to see those DNS addresses that are stored, or DNS entries I should say, that are stored on Windows, you can do an ipconfig/display DNS and you'll see all those DNS entries that are stored on your Windows PC. Okay, so if you need to see that, that's what you'll do. We have the hierarchy of servers that pop up. So basically your DNS hierarchy, you have DNS servers that are broken down into smaller pieces so they're more manageable. But you do have some that have more DNS addresses or routes to DNS addresses in them. So you're basically passing your DNS request up a tree, up the chain of command till you get to a top level, and eventually you're going to get that DNS request answered if the website exists. Okay. So what we've got here is your DNS client sending up to the cisco.com server, the local server. If it doesn't have the resolution for the domain that you're looking for, it'll go up to maybe a .com or a root DNS server that might have to bounce back to the AU or the EU for Europe. You've got CO for Colombia. So you've got different servers for different entities. So you got .com for a business or industry, org for a nonprofit organization, so on and so forth. Okay, so you basically have that DNS request passed up the chain of command and eventually it gets answered. NS lookup allows you to manually ask for DNS resolution yourself without requesting the web page. Basically, you just go into your command line, you type NS lookup, and then from there you can, well, the initial NS lookup, actually, why don't I just show you? So, here we go. So your initial NS lookup is going to show you your default server. There's my router on my network. And basically now I'm in NS lookup mode. If I want to see the resolution, let's say I want the school's website, www.hbas.edu. Okay, I see that the address for that is 166.62.84.173. So I have the actual address for Huntington Beach Adult School, or www.cisco.com. Okay, we've got some IPv6 addresses, different aliases, and the IPv4 address. So there that is. All right, so that's how NS lookup works. You're just looking for the actual IP address of different sites manually is what's going to happen. All right, file sharing, almost done. Here we have Dynamic Host Configuration Protocol, or DHCP. We get more into DHCP and setting it up on a router in CCNA 2, but for now we just need to know what it is. DHCP dynamically configures addresses, gives you information including the default gateway or gateway address, subnet mask, and DNS server. Also your IP address, of course. Manually configuring an end device is not scalable. DHCP allows for automated distribution of network information. When you get an IP address from DHCP, they are leased for a period of time. Typically, your end device will renew that lease before it expires, so your IP address doesn't just go to some other device, but that can happen still. Addresses are returned to the pool for reuse when no longer in use. So we'll be setting up DHCP pools in CCNA 2, which are just pools of DHCP addresses available for a certain network. Supports IPv4 and DHCP v6. Okay. So DHCP operation basically goes, well, you can see it down here. Your client says basically, which is DHCP discover, says I need a DHCP or an IP address. I need an IP address. And then the DHCP server says, okay, this address is available, and your client's going to respond with, yes, I'd like that address, and the server's going to say, okay, you can have it, basically. All right, so first part is I need an IP. Second part is here's what I got for you. Then your client's going to say, okay, can I have it? And the server says, yes, here is the address. Why that has to happen, why the server has to send back, because there is some small chance that your device is offered an IP address, and before it has a chance to respond, the server's offered that same IP to another device, and it responded first, so you can't get that address. Okay? If you can't have the address, then you're going to be seeing something called a DHCP NAK, no acknowledgement. The offer is no longer valid. Okay. For DHCP v6, we don't have anything here for that, but you have solicit. Got a solicit an advertisement. So solicit is going to be asking for the asking for your DHCP information. Advertisement is going to be the response. So different names, but same process. Instead, it's just DHCP solicit or DHCP advertise. Or if you're using Slack, which is what we've discussed before, you'd have a router solicitation, router advertisement that would go on as well for DHCP v6. Actually, that wouldn't be DHCP v6. That would just be Slack, but for DHCP v6, same messages. File transfer protocol is a little bit of a different one in that you have two ports being used for your file transfer protocol. It does allow you to, well, transfer files over a network, okay, push and pull files from an FTP server, Okay, so there's two connections that need to be made. There's one port used to control the traffic, to initiate and stop traffic on port 21, and the second port is for the actual transfer of data. That's port 20. These are well-known ports. You should know those ports. Okay, and if you're downloading, that's considering pulling data from the server. If you're uploading, that's considered pushing data to the server. Okay, so know those terms. Anything else here? One connection for commands and replies, one for data. Yep, we've already talked about that. So again, I think we're good there. We'll move on to the last one. I think the last one anyway. Looks like it. Last one we have here is server message block, which is a client-server sharing protocol. All of the messages share a common format, and it is part of Windows. Mac, Linux, Unix have their own implementation of server message block. Okay, so it is something that is a mainstay of Windows itself. Microsoft products now support TCP/IP protocols to directly support the server message block resource sharing. After the connection is established, the user of the client can access the resources on the server as if the resource is a local client host. Okay, so when you are accessing, I don't know, a printer through your network or accessing files on another computer in your network, you're using SMB. If you're, for instance, I can't bring that up on my computer. I don't have anything networked, but if you go browse through Windows and you're able to access another computer, that's done through server message block. Okay. Server message block can start, authenticate, and terminate sessions. It can control file and printer access. It can also allow an application to send or receive messages to or from another device. Okay, so it's a client-server file sharing protocol, and it is the last protocol that we have here in this chapter. Kind of a shorter one, so that's good. We need to get a couple chapters in at the same time, so that's it for chapter 10.